Before moving to the kinetics of rigid bodies, we need to talk about distribution of material because it is important in the dynamics of bodies. For example, if I have, let's say, 1 kilogram mass and make a shape, a rod, something like from it, and if I want to rotate it about this point, it's gonna be slightly hard to rotate it comparing to having the same thing and moving it and having it in this direction. And if I want to rotate it about this axis, of course, rotating about this axis is much simpler than rotating about this axis, right? The perpendicular axis. So nothing is different between this and this. The mass is exactly the same thing, but the distribution of material is different between this axis and about this axis, right? So we need to study that distribution, which we are going to quantify it with something which we call it mass moment of inertia about axis. What is the meaning of that? I'm going to start with the definition of it. Let's say we have a mass. It can be in 3D. It should be in 3D. It's a mass. And we want to find the mass moment of inertia of it about this axis. Let's call this axis OO. This is the definition of the mass moment of inertia. I, which means mass moment of inertia, about axis OO, this axis, is equal to integral of each piece of this mass, the mass of it, times the distance of it from this axis squared. So if I chop this mass to very small pieces like this, let's say the mass of this piece is dm, and the distance of it from the given axis is r. So I need to multiply this mass to r squared and do the same thing for every piece of this material and add all of them together. That is the mass moment of inertia. So when we are adding all of them together, it means we are integrating, right? So it's going to be r squared dm. Again, r is the distance of each piece, that dm, from the axis that we are taking, we are finding the mass moment of inertia about it. This is the definition. So more mass moment of inertia, it means your material is distributed away from this axis. And if you wanna rotate this mass about this axis, you need to give more power or more torque to your system. If I want to find the mass moment of inertia of the same thing but then another axis, like for example this one, is going to be a totally different thing because the distribution of the material about this axis is totally different than the distribution of the same material about this axis. So this is our basic definition. We are going to use this definition to find the mass moment of inertia of these different parts. Probably the simplest one is just a simple rod. So let's say we have a tiny mass, uniformly distributed rod, and I want to find the moment of inertia about this axis. Let's say the length of this guy is L, and the density of this material per length, rho density per length, or mass per length, is rho. So which means the total mass is going to be rho times L. So the total mass of this rod, if we call it M, is going to be rho times L. For any piece of this material, if you want to find the mass of it, you need to multiply rho to the length of it, right? That's the meaning of rho here. So I want to find I. So I'm going to start with, let's call this axis XX. I'm going to start with the definition of the mass moment of inertia. Ixx is equal to r squared dm. So we need to multiply each tiny piece of this material, the mass of it, to the distance squared from x-axis. So if you consider any piece, any tiny piece like this one, let's say this length is just the y, and the distance of this piece from this x-axis is y. Okay, so the mass of this piece, or the dm, is based on the definition of rho, is going to be rho times dy, right? So the mass of this piece of our body is rho dy, and the length of it from x-axis is y. So my r in this integral is y. So we are gonna have integral of y squared times dm, and dm is rho dy. Now everything is in terms of y. And how y is changing. So if you consider any small piece of this body, the y of those small pieces are going to change from negative L/2 to L/2, right? For example, the y of this piece is negative L/2. For this piece is going to be another number. For this piece is L/2. So when we are sweeping this integral element from here to cover the whole body, y is changing from negative L/2 to L/2. So the limits of integral is going to be negative L/2 to L/2. Now this is a simple integral to do. Rho is constant, you can take it out of the integral. Integral of y squared is going to be 1/3 of y cubed. So 1/3 of rho y cubed. Y goes from negative L/2 to L/2. So it's going to be 1/3 of rho times half of L cubed minus negative L/2 cubed. So it's going to be L cubed over 8 plus L cubed over 8, L cubed over 4 times 1/3. It's going to be 1/12 rho L cubed. So this is the mass moment of inertia of a uniform rod about this axis. But we usually like to write the mass moment of inertia in terms of the mass. We don't like rho. It doesn't have any immediate meaning. So to do that, I can replace rho L with mass, right? With m. Look at this. M is equal to rho L. So I can separate one of the L's. Rho L is going to be mass. So this is going to be 1/12 times m times L squared. And this is the final solution. So the mass moment of inertia of this tiny bar with the length of L is going to be 1/12 m times L squared. And let's do another one. Another simple example. Problem B1. We have the same rod. The mass is m, but we want to find the mass moment of inertia of it about x-axis, y-axis, and also z-axis, which is perpendicular to the x and y. So let's say the density of it is rho, and the length of it is L, so m is equal to rho L, like the previous example. Now we have different axes, right? In the previous example, I found the mass moment of inertia about this axis, which was perpendicular to the body, to the rod. But now we have different axes, so we are going to have different mass moment of inertias. So I would say think about this problem for 10 minutes, then come back and see how we can solve this. So I assume you did that. We are gonna do essentially the same thing. So let's say we want to find the mass moment of inertia about x-axis. So the first step, like the previous example, is choosing an integral element. So I'm going to choose a tiny piece of this rod. And let's say the length of it is the L, tiny piece. And the distance of it from the origin is small l. The mass of this piece, based on definition of rho, density per length, the mass of this piece is going to be rho dl. Now, let's start with the x-axis. So Ixx is equal to integral of rho squared dm. Same definition. What is r? R is the distance of any of these elements from the x-axis. So which is going to be this distance, right? The distance of this element from my x-axis is this. And what is this height? It is L times sine of beta. So my r in this integral is going to be L sine of beta. And dm, the mass of my element, is rho dl. So just replace that in this definition. R is L sine of beta squared times dm. dm is rho dl. So sine of beta is a constant number, a constant angle. So sine of beta is going to be a constant number. Same goes for rho. So I can take them out of this integral. Rho sine squared of beta integral of L squared dl. And in this integral, everything is about L, and it's a very simple integral to do. And what are the boundaries for L? Because we are integrating over L, so the boundaries should be about L. So look at this. When I'm sweeping the whole body using this element, L, the distance of the element from the origin, is going to go from negative L divided by 2 to positive L divided by 2, like the previous problem. So negative capital L over 2 to positive capital L over 2. Same integral like the previous one. The only thing we have different is sine squared of beta. It's going to be 1 over 12 rho times L cubed, capital L cubed. And you can replace rho times capital L with m, the mass of the rod. So it's going to be 1 over 12 m L squared times sine squared of beta. And we can do the same thing for the y-axis. The distance of my element from the y-axis is going to be small l times cosine of beta. So I'm not going to go to the details of it, but if you do the math, Iyy is going to be 1 over 12 ml squared times cosine squared of beta. And for z is a perpendicular axis to this plane, right? The distance of each element from the z-axis is going to be this distance, small l, this l. So it's going to be exactly as the previous example. So Izz, again, I'm not going to write the details, but if you do the math, Izz is going to be 1 over 12 mass times L squared.